Hello, I'm Dave Tabb. I'm a professor at Stellenbosch University in Cape Town, South Africa. I've been working in the field of proteome informatics for about 20 years, so I hope that this has a few insights that'll be useful to you. I want to start with some discussion of study design. I know it's a topic that we've covered in some of the other sessions already, but I want to emphasize this topic of batch effects. We all know that our instruments can be a little bit moody. The kind of result you get for a sample this week might be a little different than what you see in the following week. These are sometimes called in the statistical literature batch effects. Some of the biggest studies that were published in the early days of proteomics created a real problem for themselves by running all of the cases separately from all of the controls. As a result, this time difference when the two cohorts were separated masqueraded as what was a technical difference that masqueraded as a biological difference, meaning that when we saw differences between the cohorts, we couldn't tell if they were coming from the identity of the sample itself or from the fact that the instrument was performing differently. Therefore, you should always try to randomize which samples end up in each cohort if you must separate to batches. The other thing that you can do is to include a sample common across all of the batches that you must run for a given experiment. This can give you the ability to compensate for these batches when you're trying to do the statistics for a data set. The next thing I want to talk about is that there is no law in statistics that says you must do exactly 3 replicates. Frequently, we see people doing 3 replicates because it's cheaper, and this is not a very good reason, because look what happens when even a single failure takes place in data acquisition. If you have a 2-on-3 comparison, you're not going to be able to make any sort of reasonable estimate of variance, and things like t-tests suddenly fall apart. The other thing is that if we want to use a test robust against outliers, like the Mann-Whitney or Wilcoxon U-test, we must have at least 5 replicates, really, to get a useful p-value. So this tendency to run 3 replicates all the time has really got to be something we step away from as a field. I also want to emphasize that the coefficient of variation that is associated with discovery experiments, with shotgunning, is a real problem when you're trying to do quantitation. And I really strongly advise people who are trying to do quantitative experiments should use quantitative technologies, not shotgunning. Instead, they would benefit a whole lot by using selected reaction monitoring or parallel reaction monitoring. And hopefully SWATH will have similar kinds of reductions in coefficient of variation that we've already seen with tools like SRM. Now, there are a couple papers I've listed down here at the bottom, and those aren't just decoration. I tried to pick out papers that would be very, very good at covering large issues in the space of study design here. Both of those papers are very worth reading. Now, we run into this problem that frequently when we're finding differences between cohorts, we run into this problem that we must do multiple testing adjustment for the fact that we've done t-test, 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 or some other statistic. We frequently find that people make excuses for why they don't or shouldn't even use multiple testing correction. I want to face those head on. All of my hits vanished after multiple testing correction. That's the #1 complaint I get when people have used Bonferroni or Benjamini-Hochberg methods for doing a correction. You can learn more about the subject by that Bill Noble paper at the bottom. Maybe, just maybe, the null hypothesis is correct. Maybe biologically, even though the investigator thinks that cohort A and cohort B should be different, they're not. Sometimes this happens, right? So, if the null hypothesis is correct, all your hits should vanish in multiple testing correction. The other thing is that, as I've said before, people are doing too many underpowered studies in comparative proteomics. If your study is underpowered, even if the differences are there, the variation is too great for you to detect those differences. So both of these cases would explain why hits didn't survive multiple testing correction. The other thing is a sociological problem with our field. People see that a researcher who has a very big hat in our field has published a study without proper control of the multiple testing problem. So if they can do it, why can't you? Well, first off, people publish bad statistics all the time. There are plenty of very, very big names who publish very big papers that make biostatisticians cringe and die a little bit. So don't be one of them. Figure out the best methods to use and apply them, and abide by the result. Next, you also see that people creep up on multiple testing in a way that they don't realize they need it. For example, if I have 5 cohorts A, B, C, D, and E, and I compare A to B, and A to C, and A to D, and all these little pairwise comparisons within the set, I've suddenly done 10 comparisons. That's also a case of multiple testing comparison, multiple testing correction that must be done. So I urge you to use multiple testing correction responsibly, and your results will be trustworthy. And ultimately, that is one of the highest praises we can get for our field. So if I if I'm using an old software framework, should I just replace it all? Is it just timed? Should I jettison my software pipeline every 2 years? Not necessarily. After in ABRF study after study, we've discovered that people who have abundant experience with old software are generally able to produce better results than people who are trying a new software package for the first time. Your experience with the software is also a factor in how it performs. The next thing I want to say is that the higher the quality of data that you're producing, the less it matters what search strategy you're using to make sense of them. If you have an old school LTQ and you are looking at investing in multiple database search algorithms to be applied at the same time, or to build in spectral library on top of database search, you will find a pretty big bang for your buck. If, on the other hand, you have HC data with highly accurate fragment masses, you're not going to get a lot of gain from tying together different algorithms to make sense of them. The other thing is that when we do increase our IDs, maybe by 10%, we can explain 10% more of our spectra with the addition of a different pipeline. What you'll frequently see is that the new peptides you observe are for proteins that you've already observed. So your ability to quantify the proteins you've already seen will probably grow, but the depth of your catalog is not going to change that much. I think that the tool set that most people could benefit from adding most in core facilities is something that allows them to do blind PTM searching, where they don't know in advance which PTMs are viable for them to look for. There are several sequence tagging based approaches out there for this purpose, and I think that they can really help you, especially if you're dealing with samples like formalin-fixed paraffin-embedded tissues. So how should you choose a database search engine? Well, I would start by saying that there are plenty of people out there who don't have a bioinformaticist on staff, and if that's true, you're probably going to need more regular technical support. And the open source community does many things very well. It's gotten a whole lot better at making tutorial videos, for example. But I think what you'll find is that if you need to be able to call someone reliably and get an answer on why the software is doing this strange thing, commercial software has that supported a whole lot better than what you see in the open source community. And I say that as somebody who lives in the open source community. Next, I would say that just as adding different search engines is most likely to be valuable to you in low-resolution CID data, which search engine you choose is going to make the most impact there as well. Now, if I have to be a little more specific on this, I would say that the scoring techniques that are essentially a binary look at the fragment ions predicted for a peptide. This is matched, 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 therefore it scores 18, for example. That those are still quite widely used, and yet we see that the discrimination that such scoring approaches has fallen behind a fair bit. And some systems, for example, Mascot hasn't changed their matching algorithm in quite a long time. But the reality is that they've found ways to boost their scoring discrimination through subsequent analysis in Percolator, for example. So you're picking a whole system here. And I would note that having systems that allow you to do one step at a time and then drop back a step if you need to change something are probably better than those where you configure everything at the front and then 2 days later the instrument or the software has an answer for you. Having the ability to not have to repeat the database identification step, of course, can really save you a lot of time if all you need to do is change how you're filtering the differential probabilities that we have for peptides. So I was asked, how can you tell a genuine PTM or non-synonymous SNV from an artifactual hit? I would say that there are several things you can do on this. First off, anytime you have a PTM and you're trying to judge the localization, keep in mind that the closer those two potential positions are for the PTM, the less information you're going to have to make that decision, because the number of fragment ions that move is much smaller between two neighboring positions and two far apart positions in the same peptide. So always keep that in mind. The amount of information available to the software to determine where this position is really matters. Always go for the boring explanation for why you're seeing a difference. If you could explain a mass shift by being a sodium ion rather than a protonation, then go with the sodiation. We have plenty of salts roaming around in our samples despite our cleanup. Likewise, if you're doing proteogenomics and you find that a rare genomic variant could explain why you are seeing this tandem mass spectrum, but that same mass spectrum can be explained adequately by a wild-type sequence, stick with the wild-type sequence. The boring answer is a much safer, usually the more correct answer. And finally, I want to say, you know more about how peptides fragment than does the software you're using. So if you are able to read a review article by Bella Pesh, for example, on how peptides fragment, you certainly know much, much more than your database search engine about what the spectrum should look like for a given peptide. I hope that you are able to use that to protect you against falsely identifying amazing peptides. Okay, I hope that helps you very much, and I look forward to the questions. Thank you.